Today we talk about assemblies in MDTools. What I'll explain is valid for both MDTools 900 series for Solidworks and the 700 series for Inventor. I will explain how to instruct the components for assembly, and I will use this block that we see here in my video. I will use this block for assembly. As we can see on top, this is a block I designed during, I think, the first MDTools webinar in October. So we have NG16's footprint, two. We have an NG6 footprint. We have some ports. We have an orifice. Let me zoom in a bit. And there is an orifice plug, so I'll show you how to instruct the orifice plugs. We have some flanges, and we have some cartridge valves. So I will explain how to instruct each of these components for assembly. And at the end of today's exercise, we will be able to completely assemble all this manifold. Instead of taking files that I already have in Inventor format, I just downloaded from the manufacturer all the step files that I need. So I have all these files. So I show you basically a workflow where I open a step file, I instruct for assembly and save in my repository, which will be my 3D models folder. And then I'll show you my standard folder where I normally work. So let me open some of them. Let me start from the easy ones, from the plugs. So let me open some VSTi plugs. And let me open them. So in this case, nothing special. I'm just opening step files that you can find online, but what we see here is applicable to any 3D model you may already have in Inventor or SolidWorks. So when we want a component to be assembled automatically by MDTools, we need to use a following command that is called set assembly constraint. Let me highlight with a different color. And the command is located here. So inside each model, we can click set assembly constraint, and here we have 4 choices available. And these 4 choices are related to the kind of interface where this component must be assembled. We have 4 main tabs here. Cartridge valve, which is applicable to any screw-in plugs, any cartridge style component. Valve pattern, which is applicable to any surface mounted valve or flanges. Expander plug, of course, it's applicable to expanders, and orifice is applicable to orifice plugs in the form of orifice disc or plugs. Today I will use an orifice plug, screw-in plug. So this component is just a screw-in plug, so it will meet the cartridge valve requirement. And in this case, I need to select the top face, the bottom face, which will be my mating face, and the axis. When you are done, all the green icons are displayed. You can click Set Constraint, OK, and now you can save your file. I can save as and put in my 3D models and save it as a VST. Save. This component is set for assembly, and I will never need to do it again. This will be forever be assemblable by MDTools. Let me do quicker this one. I do the same top face, bottom face, and axis. Set constraint, OK. And we do a save as and put in our 3D models. And we can close. And we do again set assembly constraint, top face, bottom face, axis, set constraint, OK. And we can save as our 3D model. Let's try these components. So let's verify that they are able to be assembled. Let me first start with an assembly. So we create a new assembly. We switch to the MDTools tab. And here we have some commands that I used during the previous webinars. I am not able to do an automatic assembly because this design has not been made with a HydroCAD diagram. So I am able just to place components manually. And this dialog is asking me to load a 3D model. So I load my block. And now MDTools is displaying a list of all the cavities that are in the block. I can filter the cavities by type. So let's say that I want just the construction ports. So I have 2 XG 1x2, and let me select the CAD file. Let me go into the 3D model and take the 1x2 and move to the right. Down here, I can view a preview if I need. Okay. On the G1x8, I can select the CAD file. And if you know the file name, you can also search it, VSTI search, and then you select the one that you need. Always the possibility to view a preview of the file and move to the right and click OK. And we do the same for the third one. As you can see on top here, we have a path, and I'll show you in a minute where we set this path. So this is where we are looking for our 3D models. When you are done, you just click Assemble, and MDTools will simply load the files. As you see on the left, the files are loaded and they are assembled properly on the locations. It's very easy for any cartridge valve, but now let's look at other type of components. Let's look at flanges. So flanges are a different type of components because they need not only a mating plane, but they need 2 axes to define the orientation. So to understand how the constraints are applied for a footprint, we need to open the library manager. Let me move it here. And let's open a cavity for a flange. Let me go to SA 3000. I take one as an example, and then the same will be applicable to the other. I need to go in the edit footprint data down here. And I need to find 2 bolt holes, BH1 and BH2. So as you see, BH1 is this one, BH1, and BH2 is this one, BH2. So those are my axes. I need to define in the 3D model axis corresponding to BH1 as a first axis and BH2 as a second axis. This is important, otherwise the component will not be assembled in the correct order. If the 3D model has locating pins, this is the only difference that is now available between Solidworks and Inventor, but it will change in Solidworks in the newer version that is coming early next year. What I was saying is if we have locating pins, then the locating pins must be the axis and not BH1 and BH2. This is applicable only for Solidworks, but I will see later a footprint with locating pins. So we stay with the flange. We need to have axis 1 as a top right, looking at the flange, and the axis 2 as a top left. So let's open the flanges. And I open all the flanges that I will have in my block. And let us start. Again, set assembly constraint. That's a valve pattern. The top face is not relevant here, but we could just take this one. Bottom face is important. First axis, second axis. Set constraint. Okay, and we do a save as in our 3D model. And we can close it. Again, set assembly constraint, valve pattern, top face, bottom face, first, second, set constraint. Okay, and we can save as in our folder. Set assembly constraint, top face, bottom face, first, second, set constraint. Okay, Save as. As you see, when you have practiced a bit, it's very, very fast. You really can apply constraints very, very efficiently to components. And the last one, set assembly constraint, top face, bottom face, first, second, set constraint. Okay. Save as. Now we can close and we go back to the assembly. Let me clean a bit of the sketches. Now again, we do component. Now we can load all the footprints. Now we can load all the ports. So in this case, the flanges are classified as ports. We can sort by cavity name, and we can take 1 inch code 62 flange, and maybe one is with an open flange and the other is plugged. So we select CAD file, and we take the one open flange, and here we take the one close. For the one SA 3000 1x2, we take the 1x2 open socket, and the other is the 1x2 close. For the 3x4, we select all the 3x4 6000. Okay, and we can update all. And now we have assembled all the flanges. Since we have also all the ports and test point, now let's open the Minimesh 3D model, and the G1x2 fittings. Let's do that. Open, and we take the G1x2, we take the Minimesh, and let's take also the Orifice M8. We open it. Fittings Minimesh will behave like a cartridge valve. Set assembly constraint, top face, bottom face, axis, set constraint. Okay, and we can save as 3D models. What you see here is something that you do once, and you don't need to do any more, because next time MDTools will be able to automatically assemble the component with the assembly rules that you have defined. The fitting, set assembly constraint, top face, bottom face, axis, set constraint. Okay. Save as. And now we go to the Orifice Plug. For the Orifice Plug, we need just the bottom edge. So we take the bottom edge, which is this one, and set constraint. One constraint is enough. And we do a save as 3D models M8x1. Save. Let's go back to the assembly component, and we want to assemble to the G1x2. Select CAD file, the 3D model of the fitting G1x2. Okay, and we take all the Minimesh. Select CAD files, Minimesh, and we also have the Orifice Plug. We take the CAD model for the M8x1 and move to the right, and click OK and update. And again, now we have all the fittings, and I think I selected also this one. Probably I selected the bolt holes as well. Let's look at here. Inside here, there should be a Orifice plug. So let's move it. Move this one here, and inside we see the Orifice plug that is assembled inside that. Let me update this. Now we miss the NG16 valves, and the cartridge valve. So let's look at this DBDS. This DBDS in my library is defined as slightly different from standard cartridge valve. It is using a Sun Hydraulics style cavity. So let's go there, Rexroth, and that's a DBD20K. So as you can see here, I have defined, although this is not a sun cavity, but in our library we have a flag that is called sun cavity. That means that we want to control a cavity not by the spot face, which is normally a spot face for a standard Hydraforce or Parker or Eaton or Hidak cartridge valve. In this case, that's a cavity that has a locating shoulder. And in fact, these valves are assembled directly on a plane that is down in the cavity profile. So as you see, this is my LS. So for all the profiles that are sun cavity, the bottom face is the plane that is matching the LS. So this is important. We need to match exactly the LS. For the top face, for the cartridge, is the plane where an optional coil may be assembled. So for a relief valve, this is not important. So I will not care about where the top face is. But for a solenoid valve, the top face is important. It is the mating face where I will position a coil on top of it. So now that we understand where the bottom face is for this cavity, we open the 3D model. We open the DBD20 and convert it. And we say set assembly constraint. The top face, I don't mind. I take whichever plane. Bottom face is this one, and the axis is this. Set constraint. Okay. And we can save as our DBD20. Please remember that you can directly select entities like planes, faces, or you can create planes or axes with the Solidworks or Inventor and select them as your mating. In some cases, I found that 3D model is not very well made, so I manually created my plane and my axis to have a good matching. But really depends on the data source that you have for the 3D model. So this component is okay. Let me now open the and as assemble it component. That's my cartridge valve, and I want to select my DBD20 and assemble. And as you can see, the valve is properly assembled, and it's going inside and mating on the bottom face. Now let's look at the DO3 and DO7. We go back to our library and find the DO3, edit footprint data. So now this is important for those using SolidWorks. So far, it will change from next version, making it easier. If you are using the locating pin, this is the axis 1, and the second axis must be BH1. So it is BH2 and BH1. It is this one on top. In this case, that's axis 2. In the latest MDTools version, the 780, we simplified the way the assembly rules work. So in the previous version, also MDTools for Inventor was following the same rule. If LP was available, that is axis 1, and then the second is BH1. And now from this version of MDTools, you can always use BH1 and BH2. So BH1 is this one left, and this is the P port down here, and the second axis is this one for my library. It may change if you have changed the definition of your cavity. So let me clean up, and so I will use the axis 1 as from the P, opposite is 1, opposite to the left and opposite to the right is axis 2. Let's go back here and open the 3D model for the NG6. I have 2 stackable elements here, a reducing valve and a directional control valve. I see a question and later I'll reply to that. Okay, let's go here. This is the directional control valve. Set assembly constraint, valve pattern, top face, bottom face. P, it was the opposite, it is the first and second. Set constraint, okay, and save as 3D model, that's the 4W6. And we can close it. We do the same here. Now it's a bit challenging. You need a bit of experience, or you can measure the distance knowing where it is A. So A is this side, this is the P. So I need those 2 axes. Set assembly constraint, top face. Top face is this one, bottom, first and second. Set constraint, okay. And I can save as 3D models, ZDR. Now I can assemble component. On the DO3, I can select my 4W6 and ZDR. First, it's the reducing valve. So the first valve is the one that is making the block, and then on top you put all the other 4W6. Okay, and update. And this is assembling all. Close. And now last component, and then I jump to the questions. Last component is the 4WEH. Here it is. So let's go back to the library and look at the DO7. Now, for those using Solidworks, first axis is LP1 and second axis is LP2, because this footprint has 2 locating pins. For those using Inventor, they can either use LP1 and LP2 or always BH1 and BH2, which is easier. So BH1 is this one here, and BH2 is this one, 1 and 2. Let's locate the P port. So P port is this one. So one is looking at the valve from the top. The one is on top right, and bottom right is the 2. So let's go here. And the P port in the 3D model is this one. So we need to have the P on top. So this one is the axis 1 and the other is axis 2. Let's try. Set assembly constraint, top face, bottom face, first axis, second axis, set constraint, okay. And we can save as 3D model. The first time you do a set constraints for surface mounted valves, maybe you struggle a bit in understanding which is the correct axis 1 and axis 2. Please remember that when you create axis and planes, MDTools will create for you the axis and planes. So if at the end you made a wrong selection, you can always edit and redefine where the axis is located. You don't need to run again the interface. You just move and change the definition for this axis and plane, and it will work fine. Let's save this block. Save as, and well, I already saved it, so no need. Component, EV1, select 3D models, H4, and update all. And my block is completed. Next time, I don't need to do again all these instructions for the components because they are already set. So if I create maybe a new part, so I address that request clarification about some cavities. So let me create a block. 200 by 100 by 100. And let me place a DO3 valve. So we test if what we added now is fine. So we add a DO3 valve on top and rotate. Then we add a standard Parker C10-2 cavity. C10-2. And we put it here. And we add a Sun Hydraulics T11A cavity. Okay. I have some components that will match this cavity, so let me just copy from my 3D content to my working folder. So let me go to my working folder, and I also need my 3D models. 3D models. I take a Sun Hydraulics CBCB, and let me move it here. And I also take a Parker let me find. I don't have. Well, let me take a HIDAC. I am rushing with time, so let me take RV10A, Control C, and I move it on my 3D model folder here. Okay, let me save this block, and I save it as a test. So as we see, if we edit this standard cartridge, this one is a standard cavity. We have a spot face. The counterbore, the spot face, is where our valve is assembling. So for this kind of valves, we need to select the bottom face as the plane where this valve is assembling. For the Sun valve, the mating plane is the LS. LS is the reference, so we put it as a reference, and the LS is where we put the bottom face for the component to be assembled in the block. We make a new assembly. We run the component assembly. We take our new test block. There are 3 cavities. On the one, we load again the same valves, the ZDR and the 4W6. On the C10-2, we load that RV10A. And on the T11A, we load the CBCB HN. Assemble. And my block is assembled. If we make a cross section, let me view cross sections down here. Let me remove the colors from MDTools block. So in this case, the mating has been made on the LS directly here. This is where it has been put the constraint. This is the mating plane, LS. For the other cavity, let us go back to the view cross sections, and we put the section on the other cartridge valve. Here the mating is here. So according in the library to where which kind of cavity, if it is a Sun cavity or a standard cartridge cavity, this is where how the software, how MDTools will locate the component. Let's do an align these 2 cavities so that the cross sections will be touching both. Update. So in this case, you see the difference. A Sun cavity is assembling on the LS plane, and the standard cavity, Parker, Eaton, HIDAC, Hydroforce, whatever, is touching the spot face of the cavity. Now you're just reading. Well, the sun cavity is in the library, just an attribute that will define how the cavity is behaving. So just because when you position in the design, you want to control from the LS, locating shoulder. And when you add it in the block, you will be able to control the depth from the LS, not the depth of the standard spot face. So this is really up to you. I read the questions for all. So the question is, if we have other type of cavities, non-sun or common cavity. No, basically in our library, in terms of cartridge valve, we have the sun cavity and we have the standard. Let me go to the HIDAC 10120. This is a non-sun cavity. This cavity, when you use it in the block, it will be controlled by the spot face, and the sun cavity is controlled by the locating shoulder. This is the only big difference. In terms of assembly, what implies by using sun cavity versus standard cavity is where you put the bottom face. For a sun cavity, the bottom face must match the LS plane. For another standard cavity, non-sun cavity, let's call it non-sun cavity, you need to take the spot face plane. We are running out of time. I show you just one small other setting that will make the assembly for the plugs being very, very fast, immediate. What I did for all the plugs in the beginning of my webinar today, once you do, you can directly link the 3D model with the plugs in your library. As you see here from the settings in the library manager, so on the settings, I have a plug model library, and this is where I have my plugs in my library. And when you can select any different folder for the plugs. When you go to the plugs folder here, you can link to each cavity a plug that lies in a particular folder. So as you can see here, when I select a cavity for the plug, I can see the preview of the 3D model, and I can link directly in the library each plug with a corresponding cavity. The big advantage here is that to assemble all the plugs in a block, instead of doing manually the selections that I had done, I can just click one command that is called plug, and this command will automatically assemble all the plugs. As you can see, I have all the plugs assembled. So what I did manually here, component, select the cavity, and select the 3D model, for all the construction parts can be fully automated just by linking the 3D model to the corresponding cavity, so that really you save a huge time in assembling all the construction plug. It's just one command, and it will load all the 3D models that you need and place the plug in all the cavities that requires a construction plug, no matter if it is a expander or a screw-in plug. The last piece of information is that if you need 3D models for plugs, expander, SA plugs, short ports, BSP plugs, you can find them in this website, Fluid Power IT. They are both in Solidworks and Inventor versions, and they are already set for assembly rule for plugs. They are already set for assembling. So if you go to fluidpower.it, you will find a link to download the 3D models working for Inventor and Solidworks for MDTools to be assembled. Also MPTF, metric, SAE, expander, and BSP. You may have already the 3D model, so my recommendation is you instruct your 3D models like I did. But if you don't have 3D models, feel free to use those that you find here.